Okay, welcome to the Unit 4 review. In this first problem right here, they're going to give you a function and simply ask you what is the domain, the range, and the zeros. Alright, so, you have a graphing calculator at home, and you could put this onto your graphing calculator and see everything you need to answer this question. At first, I'm going to show you how to do this by hand as well. Alright, and again, it's that focus on visualizing a function. So when I see something like a y equals the square root of 9 minus x squared, I'm thinking, isn't that a semicircle? And here's how I see that. Alright, well, I have an x squared, but it's underneath a radical. And if I squared both sides to get rid of that radical, alright, look what would happen. Okay, and this is where I'm trying to get to right there, but let's go ahead and do that right now. So y squared, and if I square the radical, I can just drop it, is 9 minus x squared. And now you add x squared to both sides to get x squared plus y squared equals 9. So this equation right here, alright, when I square both sides, I get the equation with a circle centered at the origin with a radius. See that r to the second power? That's the radius to the second power. So the radius would be 3. So what would that look like? Well, look at this little window right here. And there's my circle right there. It's a circle again, centered at the origin with a radius of 3. Now, that is the graph of x squared plus y squared equals 9, which is a circle. All right. Note that I said that this would be a semicircle because the circle would have to have a plus or minus in front of that radical, but we don't have that. That means we just have the semicircle, the positive part of that graph right there. And there is my perfect graph right there. And now I could look at that and do the domain, the range, and the zeros of the function. Now, if I decided I'd just put this onto my calculator as y sub 1 equals radical 9 minus x squared, my calculator would give me this in a standard window. Now note, that doesn't look like a perfect semicircle, but this is a rectangular window right there, and I did not square it. I didn't have to because I see everything I need right here. The domain, and again, you see it right here. The domain are all the x's on this graph right there. And we're talking domain, we're talking x's. And the minimum x value, I could use my graph on my calculator or the one I did behind. By hand, would be negative 3. So negative 3 is less than or equal to x, and x is less than or equal to positive 3. For the range, well, the range would be my y interval in that graph. We're talking y's here. And a minimum y value right there is a 0. The maximum y value is a 3. And then the zeros of the function. Well, that's where the graph touches the x-axis. And I see 2 of them by hand over here on my calculator. All right. And at the zeros, the y coordinates will always be 0. So there's my y equals 0, and look what I have. An x equals negative 3, and an x equals positive 3. I'm going to represent both of those ordered pairs right here, just like this, with a plus or minus 3. And that's the first type of problem you're going to need to do on your tests. They're going to give you a function and ask you for the domain, the range, and the zeros. Okay, for the second problem of the review, they've given you a graph that has the function g of x, which is linear when x is less than negative 1, and then it's quadratic when x is greater than or equal to negative 1. And again, same thing, we're going to find the domain, the range, and the zeros of g. Okay, so at first I'm going to graph this by hand, and I'm going to do that because if I graph it by hand, I think I get a much clearer picture than if I use my calculator. But you can do either. So let's see if we can do this by hand now. All right, well, what does x plus 1 look like? That's a line with a y-intercept of 1 and a slope of 1. So I'm going to go up 1 and over 1, put another point right there. Now, the line through those 2 points is defined for all real numbers. but I need this line in the interval x is less than -1. So I'm picturing that line right now, but I'm only going to begin it at -1. So I'm going to put an open dot right there. And I'm going to graph this like this so I can see the whole thing. But notice how I did, solid when x is to the left of -1, when x is less than -1, and then I did dashed when x is to the right of -1, and the solid dot on x equals -1. So that is the perfect graph of x plus 1 with the restricted domain x is less than -1. Now, how about the quadratic? Well, let's just picture the entire quadratic right now. And the parent function for 1 minus x squared would be x squared. And you all know what that looks like. A parabola opening upward with vertex at the origin. But there's a negative in front of that x squared, which is going to take that parabola and reflect it in the x-axis. So now it's opening downward with the vertex still at the origin. But then we have to add 1 to that, which is going to slide the vertex up 1 unit. So my vertex of the parabola is going to be at the y-intercept 0, 1, right there. All right. And then what are the zeros of this parabola? Well, when does 1 minus x squared equal 0? When 1 equals x squared, or x equals +1 or -1, right here and right there, which worked out perfect because now here's my parabola. It's going to come up, hit the vertex and work down. And I'm going to do the whole parabola, but I'll put the stuff that's not within the restricted domain as dashed. And there it is. And that's the perfect graph that's going to make it very easy for me to answer this question. Now, I could have used my calculator and done the linear function as x plus 1, so that's y sub 1 equals x plus 1 right there. And then y sub 2 is the 1 minus x squared. But because I can't restrict the domains on my calculator, it's not as easy for me to see as this over here. As long as you're aware of the restricted domain for the linear and the quadratic, you can see it there too. But I think it's much easier to see over here. So the domain, well, do you see the arrow? This is going forever to the left and forever to the right rather slowly. So the domain x would be in the set of real numbers. The domain is all real numbers. And that double bar R is the symbol for the set of real numbers. What's the range? Well, there's all my y values, or in this case, we'll call that g of x if you want. So g of x, let's see. Well, the maximum of this function g of x is at y equals 1 right there. So it looks to me like g of x is always less than or equal to that 1. And the zeros are -1 and +1, which are, let's write those as ordered pairs. Okay, the y is 0, and then I'm going to write a negative and a +1 as my x coordinates. Right there. And that's number 2. Domain, range, and zeros. Be an expert. Try to be able to do them by hand, and if not, go to your calculator. You can get it either way. Okay, number 3. Let f of x equal the quadratic x squared plus 2x, and let g of x equal the linear function x plus 2. Now we're doing operations with functions. We're going to add them, subtract them, multiply them, and divide them. So this is very, very simple algebra. F plus g of x. Let's add the two functions together. So I'm going to take the function f of x, which is x squared plus 2x, and I'm going to add to that g of x, which is nothing more than x plus 2. And now we simply combine like terms to simplify. So I have 1x squared plus 3x's plus 2. And that is f plus g of x. How about f minus g of x? Well, now we're going to subtract them. So you start with the x squared plus 2x again. And now we subtract the g of x. Now this is very important when we're subtracting. We need to put the g of x within parentheses so we remember to distribute that minus to every term in g of x. So let's simplify this one now. So I have the 1x squared, but now look at this. I have 2x minus an x to give me 1x plus x. And now we've got the minus the positive 2, so that's a minus 2. And there it is. F minus g of x is x squared plus x minus 2. Now we multiply them. So we're multiply it out, so just FOIL it out like you always have. So equals x squared times x would be x to the third. And the outside would give me a 2x squared. The inside would give me another 2x squared for 4x squareds. And then my last terms would be 2x times 2 or plus 4x. And there we go. F times g of x is x to the third plus 4x squared plus 4x. Now, f over g of x. Let's divide the functions. So f of x is in my numerator and g of x is in my divisor. Now, we need to simplify this one just like we did everything over here. All right, so look at your numerator. Can you factor anything? Well, I see a common factor of x in my numerator, so I'm going to factor that out. And distributive property, x times x will give me the x squared, and x times plus 2 would give me the 2x's. And now look what happened. The factors of x plus 2 cancels out, leaving our x. But now, do you notice the comma right here? When you are dividing functions, usually you have a domain restriction, because what number can we not divide by? We can't divide by 0. Now, x looks like it's defined for all real numbers, right? But you've got to go back to your initial substitution before you simplified. Do you see that there's an x plus 2 in your divisor? That implies x cannot equal negative 2, because negative 2 plus 2 would be 0, and we cannot divide by 0. So I'm just going to say x cannot equal negative 2. And there you have it. Make sure you know how to add, subtract, multiply, and divide functions. And usually in the division, you're going to have a domain restriction. Okay, number 4, we're going to do a couple composite functions. So they give you f of x equals x squared plus 2x, and g of x equals x plus 2, and they are asking you to find, what does this mean? F composed with g of x. Now you can write this like this, or f of g of x, same thing right here. Now you guys have typically used this notation, so if you look at this notation, f of g of x, what does that mean? Well, we're going to take the function f, but instead of f of x, we have f of g of x. And what is g of x? X plus 2. So that tells me I'm simply going to take this function f, but I'm going to replace every x with the quantity x plus 2. So x squared plus 2 times x becomes x plus 2 squared plus 2 times the quantity x plus 2. Now, all we have to do is simplify this. So let's go x plus 2 times x plus 2 would be x times x squared. And then your outside and your inside would give you a 2x and another 2x for 4x's. And then your 2 times 2 will give you a 4. All right, and now here distribute the 2. So plus 2x and plus 4. Okay, combine like terms. So if I look at this, I see I have 1x squared. How many x's do I see? 4x and 2x. That's 6x. And then I have a 4 plus 4 is an 8. Now, usually composites can have some domain restrictions because x has to be in the domain of the internal function g, and g of x has to be in the domain of f. But both g and f are polynomials which are defined for all real numbers, so we're not going to have any domain restrictions whether we're talking about f composed with g of x or b g composed with f of x. So all this is find the composite and simplify. So let's go to g composed with f of x, and if you want, write that g of f of x. And now let's take the function g, but instead of g of x, we now have g of f of x, which is x squared plus 2x. So now I look at my g of x, and I've got to replace this x with x squared plus 2x. So there's my plus 2 right there, and this x becomes x squared plus 2x. And look, I'm already simplified, and that is number 4. That's how we do composites. Okay, number 5. Determine whether the graph of x squared minus xy equals 4 has symmetry in the x-axis, the y-axis, the line y equals x, or the origin. So our rules for symmetry right here. Now, it's pretty simple, and I have all the official tests right here on this hyperlink. There they are. But you know what? I'm gonna do this a little more efficiently with you. We went through all this when we did the original lesson, but let's go back and make it even more concise. All right. So if I want to check to see if this relation has symmetry in the x-axis, all I have to do, well, picture that, symmetry in the x-axis. That means if I change this y to the opposite of y, so every y in the relation goes to the opposite of y. If I do that substitution and I simplify and get exactly the same equation right here, then I would have symmetry in the x-axis. So let's do that. So this y right here now becomes the opposite of y. But now when I simplify that, I get my x squared, and negative x times negative y would be plus xy equals 4. Not the same equation. Therefore, this relation, if you want to call it a relation or equation, does not have symmetry in the x-axis. How about the y-axis? Well, now, to reflect in the y-axis, every x should be able to go to the opposite of x and then get the same equation. So I'm thinking x goes to the opposite of x. So let's do that substitution. So this x now becomes the opposite of x, note the parenthesis, and this x becomes the opposite of x right there. Now let's simplify and look what we have again. I have negative x squared would be x squared, and minus a negative x times y would be plus xy again equals 4. Not the same equation, so this equation does not have symmetry in the y-axis either. How about the line y equals x? Well, here, for symmetry in the line y equals x, that means we can interchange the variables and get the same equation. So every x becomes a y, and every y becomes an x. Now watch how I wrote the rule here a little more concisely. So every xy goes to yx. So let's do that and see what we get. All right, so the x squared now becomes a y squared, and the negative xy now becomes a negative or minus yx equals 4. Now that's obviously not the same equation. I mean, some people, I'm a little OCD, so I'm probably going to write that minus yx is minus xy. So let's just do that. Y squared minus xy equals 4. Obviously not the same equation again. So this equation does not have symmetry in the x-axis, the y-axis, or the line y equals x. Now, let's make sure we check the origin. Don't just assume it's the origin now, because this is a good way to check all of your other work as well. Let's see what happens here. The origin. Well, for symmetry in the origin, all right, every x can go to negative x, and every y can go to negative y, and still give me the same equation. Look how I wrote that. Every point xy on the graph of this relation right here, I can make them negative x, negative y, simplify, and get the same equation. All right, so this x squared becomes negative x squared, and then I've got minus x becomes negative x, y becomes negative y, and look at that. If I simplify it, negative x squared becomes an x squared, minus a negative x times a negative y becomes minus xy equals 4. That's the same equation right there in simplified form. So guess what? This relation right here, all right, has symmetry in the origin. Okay, number 6, sketch the graph of each of the following. Well, let's begin with part A. Y equals 2 times f of x. Well, f of x is given as this piecewise linear function right here. And if we take that function and we multiply it by 2, that means we're multiplying the output or the y coordinate of every point on this graph by 2. So let's just pick some key points like the endpoints of each segment and double the outputs of each of these points. So you see right here that the y value is 2. If I multiply by 2, that's going to become a 4, and the x coordinate does not change. Here I have a y value of 1, so that's going to jump up to 2. Another y value of 1 jumps up to 2. The zeros, well, 2 times 0 is 0, so that point's going to stay there. That point's going to stay there. This is a negative 2, so it's going to drop down to negative 4. And this is also a negative 2, so that's going to drop down to negative 4. And now I do nothing more than connect the dots. And this blue piecewise linear function is my picture of y equals 2 times f of x. Isn't that cool? Now part B. Let's do the absolute value of f of x. The only thing this absolute value is going to do to this function f of x is take the negative branch right here, which is negative, and if you take the absolute value of a negative number, it becomes the opposite positive number. So all I have to do is take this branch of the function and reflect it in the x-axis. That branch right there, reflected. And now let's rewrite the graph. So this part all stays the same. And then when I get here, I'm going to go up and out. There it is. Perfect. Okay, part C. Y equals the opposite of f of x. All right. Well, that's going to take this entire piecewise linear function and reflect it in the x-axis. So we're just flipping over the x-axis. All right. So the part that is 0 stays 0. These positive branches become negative, and these negative branches become positive. Picture it. There you go. One more. And my favorite, by the way, y equals f of x plus 2. Well, if I add 2 to every x coordinate in a function, that's going to be a horizontal translation. And we always go the opposite direction of this symbol here, the sign plus. So I know I'm translating to the left. And how far? 2 units. So let's just slide this piecewise linear function 2 units to the left. Picture it. There you go. All right, great problem. Okay, number 7. They give us this beautiful graph of y equals g of x, and they're asking you what is the fundamental period of g. So I'm looking for a pattern. I begin on the y-axis and I think about how far I have to travel horizontally until the pattern repeats. Well, it looks like this part of the graph is the entire pattern that I could have translated to the left and put the whole thing right on top like that. So I'm going to say that this has a period of 1, 2, 3, and 4. What is the fundamental period of G? 4. Okay. Now, I like to think of this going on forever in both directions, the same pattern, but that'll work. B. What are the maximum and minimum values of G? Well, the maximum y value of this function would be up here at a 4. And the minimum value of this function would be down here at y equals 1. There's my max and my min. And I'm going to use that for my amplitude, because amplitude is half of the range of the function. And there's a very simple formula for that too, by the way. It is the maximum value of the function, capital M, minus the minimum value of the function, that's a lowercase m, divided by 2, which is, by the way, half of the range. So, max minus the min. Well, look at over here to the left. There's my max, there's my min. 4 minus 1 is 3 divided by 2. and that's the amplitude. So make sure you can find the fundamental period of a function, you can find the maximum output, the minimum output, and tell me the amplitude. All right, number 8. Describe and illustrate what happens when the graph of a periodic function with period p is horizontally translated p units. Well, if I translate a periodic function with a period of p units to the left or to the right, I'm going to translate it right on top of itself. Okay, then use the definition of a periodic function to explain why this happens. All right, well, here's what's going on. Now, I want to take you where you've been and where we are going. This graph right here, you've seen this before, and we're going to work most of second semester with trigonometry. I hope you recognize this as y equals sine of x. And this is a trig window right here where that first hash mark is pi over 2, pi, 3 pi over 2, and 2 pi right there at the end. Now look at this graph. Do you see the part of the graph in quadrant 1 and quadrant 4? That pattern is being repeated over and over again forever in both directions. So that tells me that the period of y equals sine of x is 2 pi. That means if I graph y equals sine of x minus that period, or I could go plus, by the way, too, it doesn't matter, 2 pi, I should get exactly the same graph because it's taking this entire graph and sliding it 2 pi units to the right. So picture like this max right here. If I slide 2 pi units to the right, that's going to end up right there. All right, look at the 0. Maybe easier to see right there. This point's going to slide 2 pi units and right there, and we just begin the pattern again. And let me get out my calculator and let me graph this. I guarantee it's going to be exactly the same graph as y equals sine of x. And look, there it is. So, explanation. Because it is being translated horizontally by its fundamental period, the graph does not change. It just slid right on top of itself. We're looking at exactly the same picture. Okay, number 9, part A. Which of the two functions f of x equals root 3 plus x squared and g of x equals 3 plus x has an inverse? Find a rule for the inverse. All right, well, for a function to have an inverse, we should be able to interchange the variables and then come up with a function if we solve for y. So let's take this f of x equals root 3 plus x squared. And let's interchange this variable. So this f of x is my y. It now becomes an x equals 3 plus, and this x right here now becomes a y. Now let's solve for y and see if we have a function. So solve for y. Well, if I'm going to solve for this y here, I better get rid of the radical. So I'm going to square both sides. So I've got x squared equals 3 plus y squared, which means y squared would equal, and what would we have to do is subtract 3. So y squared has to equal x squared minus 3. And now we have to get rid of the square, so let's square root both sides. The square root of y squared is y equals, and when we square root the other side, we have to talk about the positive and the negative root. Don't forget that, plus or minus the square root of the quantity x squared minus 3. Now this plus or minus right here tells me that this is not a function. All right? So it's not a function. Therefore, f of x equals root 3 plus x squared does not have an inverse. Well, let's check g of x then. By the way, and let me show you this. If I graph this function right here, guess what I get? There it is right there. And graphically, to see if I have an inverse, to have an inverse, the function must be 1-to-1. It must pass the horizontal line test. F of x is not 1-to-1 because if I drew a horizontal line just about anywhere, it's going to cross it at 2 points. Therefore, it does not have an inverse function. Okay? We can reflect over the line y equals x and do stuff like that, but we're not going to get a function. Now, g of x. Let's interchange the variables again. So this y right here now becomes an x equals 3 plus, and this x becomes a y. Again, solve for y. Y equals, and what will we do? Subtract 3 from both sides, x minus 3. All right. Now, there it is right there, and that is a function. That's a line right there with a y-intercept of -3 and a slope of 1. Okay, so that's a function, so therefore it is the inverse. But we can't write the rule, see the find a rule for the inverse? We can't leave it y equals x minus 3 because this y is actually the inverse of g. We've got to use the proper notation. So instead of saying y equals x minus 3, I've got to write this, the inverse of g of x equals x minus 3. And there's my rule. Okay, so now, and let's check this on our calculator. So if I graph this function and this function, they should just be reflections of one another over the line y equals x. And look at that. Here's my line y equals x. Here's my original function, g of x equals 3 plus x. And here is my inverse, g inverse of x equals x minus 3. They are reflections of each other over that line y equals x. So explain why the other function does not have an inverse. Well, we already did that down here, really. F of x is not a one-to-one function. It does not pass the horizontal line test. Okay, number 10. The area A of a triangle is a function of the base b and the height h. So this is a function in two variables, area. Area depends on the base of the triangle and the height of the triangle. So express A as a function of b and h. So all they want you to do here is use the appropriate notation. So area as a function of b and h is a of b comma h, a function in two variables. And what does that equal? Well, what is your area of a triangle? Base times height divided by 2. Or 1/2 base times height if you prefer. Part B, find a of 3, 4. This is just direct substitution. So my base is 3, my height is 4. 3 times 4 is 12 divided by 2. That would be a 6. And now my base is 6 and my height is 5. 6 times 5 is 30 divided by 2 is 15. There you go. Now draw the curve of constant area. A of b comma h is 3. Now I know this graph h has to be vertical and b has to be horizontal by the notation, but they even guided you a little farther and said in a BH plane. Guess what? I already know what that looks like, and I hope you do too. All right, so what we want to do though is just do substitution. So my area is 3, so that means 3 has to equal the base times height divided by 2. There you go. Now, since h is my dependent variable, now I've got to solve this for h to graph it. So if I'm going to solve for h depends on b, and I see it here and I see it there. So h equals, well, what would you do first? Multiply by 2 to get a 6 and then divide by b. So h has to equal 6 over b. Now whenever I have any positive number over my independent variable, that's going to give me what? Inverse variation, and you know what that looks like. Okay, in the BH plane, it's just going to be a first quadrant graph that has this shape. So, and if you don't see that and you don't want to take a chance, just call that h y sub 1 and break out your calculator. Let the b be x. Guess what? There it is right there. All right, number 11, a cylindrical tank 4 feet in diameter. Well, let's look at this diagram. And the first thing I'm going to do is input given information. So if the diameter of the cylinder is 4, then this radius right here would have to be 2. And it fills with water at a rate of 10 cubic feet every second. So we're filling this with water. 10 cubic feet every second. This is a big cylinder. So the volume of water in this tank is going to be 10 times the number of seconds I fill it. but I just call that 10t. Then it says express the depth of the water in the tank. So I'm going to draw this picture here. Check it out. This is filling up with water. Okay, oh, before I do that, let's go. What's the volume of a cylinder? It's area of the base times the height. Well, the base is a perfect circle, pi r squared times the height, pi r squared h. So volume is pi times radius squared times h, and the volume of water in this tank is 10t. Those would have to equal each other. And look what they're asking you to do. This is way easier than it looks. Express the depth of the water in the tank as a function of the time t in seconds. So I'm going to draw that. There it is. There's my water level. And they want this depth. They want this right here, which I'm going to call h of t. Okay, the height of the water in this tank. Okay, so express the depth of the water in the tank as a function of the time t, h of t, in seconds. Assume that the tank is empty at t equals 0. So all we have to do is set these two volumes equal to each other. All right, so pi r squared h, and by the way, the radius is constant. It's always 2. So 2 squared, that's a 4 pi h, has to equal the volume of water in the tank, which would be 10 times the number of seconds t. And now, h in terms of t. Solve for that h. So h equals, well, we have 10t on the right, and we've got to divide that by the 4 pi. And let's just simplify that. So 10t over 4 pi would be, what, 5t over 2 pi? There you go. So, one more time, express the depth of the water, which we're calling h of t, in the tank as a function of the time t in seconds. So, h of t equals 5t over 2 pi. All there is to that. Pretty darn cool. Okay, here's our last problem. Again, like number 11, this looks way more complicated than it is. You know, let's use all the tools that you have and your critical thinking skills, and you can make this a piece of cake or anything like it. So, number 12, triangle OAB. So that's this, looks like it's an isosceles triangle with a vertex at the origin right there. Let me see. Oh yeah, it is an isosceles triangle with vertex O and vertices A and B. There's A and there's B. On part of the parabola, y equals 9x squared. So they're saying point A and point B are on this parabola, y equals 9 minus x squared. Okay, that is above the x-axis. Okay, cool. So what do they want us to do with this? Oh, here we go. Express the area of the triangle as a function of the x-coordinate of A. Okay, well, let's start with basic. What do we know? Area of a triangle is what? The base times the height divided by 2. Okay, well, the base of this triangle is that segment AB right there. And I've got to write this all in terms of x, don't I? The x-coordinate of point A right there. Well, if this is x units, then over here I'd have to have x more units. So isn't this entire base right here nothing more than 2 x's? There it is. All right. And what's the height? It's this distance right here, which, by the way, is the y-coordinate of point A. And what is that y in terms of x? That's 9 minus x squared. So the base is 2x, and the height is the quantity 9 minus x squared divided by 2. Okay? I'll simplify that a little bit. I'll cancel out those 2's. But I think I'll just leave this now in factored form. Okay, so there's my area in terms of x. A of x, or area of this triangle, in terms of the x-coordinate of point A, is x times the quantity 9 minus x squared. Part B, what is the domain of the function? Well, I can see the domain, all my possible x's, in this lovely graph right here. X can range from 0 to 3 exclusive. Right there. my x's have to be somewhere along this segment other than the endpoints of that segment right there, because if x was 0, I wouldn't have a base of the triangle or anything there. Okay, so it's got to go from 0 to 3. Okay, use your calculator to find the max. Now look at, I have my area function in terms of x. I have my restricted domain. X has to be in the open interval from 0 to 3. So this is y sub 1, and I put that on the window from 0 to 3, and I will get the perfect graph. There it is right there. And now you guys know how to find the maximum on your calculator. All right, and that would be the y value of that point right there, which happens to be 10.39. So I'm going to say that the maximum area is approximately, and I could round that to whatever I want appropriately. I said 10.4 square units. And that's the last problem. Look, these challenging problems are really quite simple. All right, I hope you guys enjoyed the review. Get a hold of me if you have questions. Test is coming up. Have a great day.